Hey everybody, we're going to look at section 4.3. This is doing hypothesis tests for a population mean when the population standard deviation is known. Okay, so we're going to jump right in. I think we'll do the first and last question. So here's question 1, and it just walks through sort of the process. Usually I set up an alternative hypothesis first, so you have to pick mu is greater than a value, less than a value, or just not equal to a value. And that'll be somewhere in the wording of the problem. You have to make out which one of these they're talking about. And then for the null hypothesis, we just say mu equals the value, the same value that's used up here in the alternative. Okay, and as we've talked about before, the alternative hypothesis determines what kind of test that you're doing. So greater than problems in the alternative hypothesis are right-tailed tests. The less than problems here are left-tailed tests. And then when you say not equal, that means less than or greater, so those are two-tailed tests. Okay, so we'll go ahead and jump on in. There's no context in this problem, so it's a little easier in that sense. Okay, so it says from a random sample of size 59, a sample mean of 33.5 is observed. I'll go ahead and make a note of that. Oops. Okay, and our n again was 59. Go ahead and put that down. Okay. It says assuming a population standard deviation of 9.5, so that's our sigma, 9.5. It says to test a claim at 4% significance, okay, so that's our alpha, is 0.04. Test a claim that the mean is greater than or more than 30.7, so that's an alternative hypothesis. They're saying that the mean is more than 30.7. And I usually figure that out first, but generally we would write the null hypothesis before it, so I'll make a little space up there. So the null hypothesis, we're actually assuming that the mean is equal to this number, 30.7. So you just change it to an equal sign, and that's the assumption we make. So I think we're good here. At some point, they're going to have us check the criteria for normality, but that'll come up here. So first of all, there's no mu on your keyboard, so on this little palette that pops up, you'll have to say mu, and then equals, and 30.7. Like that. That's how you have to do that. And then with the alternative, it was mu greater. So again, I'll click on mu in the palette, and then greater. 30.7 looks great. And because it's pointing to the right, this is a right-tailed test. I think I'll make a note of that on here. Okay, now this whole issue of the criteria for approximate normality, your sample size needs to be bigger than 30 or the population has to be normal. So if you look up, our sample size was 59, that's greater than 30, so we can put our little check mark down. And yes, the criteria were satisfied because the n is bigger than 30. There's also a check you can choose for when the population you're sampling from is normal. Anyway, we're okay here. And then at some point we need to compute this z-score. It's just the z-score of your sample mean to see how many standard deviations that it lies from the population mean. So we'll go ahead and do that here. Okay, so x bar is 33.5. Mu is is we're using 30.7. Okay, over standard deviation 9.5. Over the square root of n, that would be the square root of 59. Okay, so that's the computation. And then over to the calculator. Okay, so, and it'll want us to round this to 2 places after the decimal, I think. So we'll go with 2.26 approximately. Should be okay, as long as I didn't type anything wrong. And we'll check it, and it must be okay here. So that's great. Next, we're going to do a critical value, which will determine if this is statistically significant. You need your level of significance here. It's 4%. So for alpha, I'll go ahead and put in a 0.04. And then we're going to have to look up that critical value in table A2. Okay, so again, 0.04, it's a right-tailed, but a one-tailed test with a 0.04 alpha. So we'll just slide up here. Okay, so alpha's 0.04 one tail. So we're in this column of the table. We'll go to the bottom row where the z-scores are. So I think you can see what I've got here. 1.751 is our z critical value. Okay, so I think I'll clean that up. 1.751, don't forget. Okay, so the z critical value, I'll do this with a CV. CV is 1.751. Okay, and maybe just I'll just sketch a little kind of a cheesy diagram here. And just a kind of quick reminder how this works. This critical value is right here at 1.751. And when this test statistic, the 2.26 here, if that lands into the tail, and it is in the tail here, then we consider that statistically significant. Okay, so let me shade that in real quick here, just to make the picture real pretty. Okay, so I think we can pop back to the problem here, and make some space. Okay, so I think that is probably, there we go. Okay, so the z critical value, we put 1.751 down. And the statistic we decided is in the tail, so it is statistically significant. Yes, significantly greater than the assumed population mean. We're good to go here. Next is a p-value. So I'll do one more little bell curve. And we'll sketch in how the p-value will look. So now this is just a little deeper into the tail, so that's our 2.26, our z-test statistic. And I'm going to shade that tail. It goes on beyond what I've drawn, but it's something like that. Okay, and the area there will be our p-value. Okay, so we get that on table A1. All the p-values come from a probability table. Table A1 is a probability table, so let's jump over to there. Here it is. So our z-score is 2.26. So here we go, 2.2, 0.06. I think we're going to have 0.9881. Okay. Don't forget, 0.9881. The area to the left is 0.9881. Just remember how that table works. This is a right tail test, so we need the complement of that. So our p-value is going to be 1 minus 0.9881. So we'll check that real quick. Okay, and we get 0.0119. Okay, and so we can, I think we just put that in here. Hopefully we'll get it right. 0119. And it looks like we got it right. And now we're just going to kind of draw the picture that I drew over here. One of these, I guess. So I'm supposed to put in my test statistic here. So the test statistic was 2.26 there. You can see this red line here is the critical value at 1.751. So this has gone past the critical value. The pink area here is the alpha value. So the blue area is the p-value, which you can see is 0.0119, and that's exactly what we got. Clearly the p-value in blue will be less than the level of significance alpha in pink. Okay, so I think we check that and move past it. Okay, so as we said, whenever the p-value is less than alpha, we reject the null hypothesis and support the alternative. So here our p-val, let me go and put this down, the p-val. I'm just going to give you 2 digits in green, and then I'll obscure the rest sort of by writing in gray. So 01 and then a very faint 19. We're just focusing on the 0.01, which is less than 0.0, what's alpha? 0.04. That's our alpha. So less always means that we reject the null hypothesis and support the alternative. Okay, so we'll just click on that right here, and we're good to go. So that's it for that problem, I believe. All done. Okay, and we got, hopefully, we got 6 out of 6. Okay, good. And then I just want to go ahead and I'll take a moment and clean up, and then we'll come back and do question 7. Okay, so I've got this all cleaned up. We're going to jump up to question 7. This is going to be similar, but it's going to be in, this time it's going to be in context, and I don't think it's going to be a right tail test. So here it comes. It says, over the last decade, the mean age of students at Mount San Antonio College had been 24 years. With many social changes over the last few years, it was wondered if this average age had changed. From a current random sample of 281 students, okay, there's our N. I'll go ahead and say this is bigger than 30. Put our check mark down, so we're good to go there. The mean age was 25.2. That's from a sample, so X bar is 25.2. Assuming the population of student ages at this college is normal, which I don't actually need, but it has a standard deviation of 8.4 years. Okay, so the sigma is 8.4. Tests a claim at 5% significance. Okay, alpha is 0.05. That the mean age at Mount San Antonio College has changed, which means it's different, which means it's not equal to the previous average of 24. So it's not 24. That's your alternative hypothesis. So the null is that it is equal to 24. Like that. Okay. I think we walked through the first few questions here. So the null hypothesis, again, you have to use the palette. Mu equals, there's no equals on there, but mu equals 24 is the null hypothesis. And then check that. And then here, this one's a multiple choice. So the alternative hypothesis would be mu is not 24. Okay, we figured that out. Whenever you have a not equal, just a quick reminder, this makes it a two-tailed test. Okay, and so we'll say it's a two-tailed test. Okay, and are the criteria, excuse me, are the criteria met? Well, we actually had two things happen on this. It did have a sample size bigger than 30, but also the population was normal up here. So we can say both of the criteria were satisfied, and you only need one. So it says, yes, the criteria are satisfied since the population we're sampling from is normal and n is bigger than 30. So that's great. Two criteria met. You only need one. Okay. And now we're ready for our test statistics. So I've already got the formula here. We'll just start plugging in numbers. So X bar was 25.2. We're using 24 for the mean, the population mean. Over the population standard deviation, which we're using 8.4, it says. Over the square root of our sample size, the sample size was 281. Okay, so let's run those numbers. Okay, and it says that we should do this to two places, so we'll go with 2.39 on this. Okay, and I'll plot that after I figure out my critical values. So I'm just going to put this in here. 2.39. Let me check it. Looks good. Our level of significance is 0.05 apparently. Okay. And now this is a two-tailed test, so there's going to be a left tail and a right tail critical value. So we'll look those up with a 0.05 and two tails. So let's just pop over here to table A2. Okay, so again, our alpha is 0.05, but two tails right here, all the way down. And this is one we see a lot. It's 1.960. Okay, so I'll clean that up. Oops. There we go. Oops. Okay, so again, it's a two-tailed test, so technically we want to do plus or minus on the critical value. Okay, so I'll just do one on the left and one on the right. Negative 1.96 and a positive 1.96. Okay, and our looks like our test statistic is out in the right tail again, so that will be considered statistically significant. Okay, so yeah, it's significant. Okay, and then we need to do a p-value. I guess I should put these in. So the negative critical value, negative 1.96, right tail 1.96. And because the test statistic is in the tail, we're going to say yes, it is significant. Okay, and then a p-value. Okay, so for the p-value, we've got to put in our 2.39 here. It's going to be a little further out in the tail like this. Just keep in mind it's a two-tailed test, so you actually have to do both sides. They're going to have the same area. So really, I'm only going to do one, and then I'll double it. Okay, so we'll go to table A1 to look up the 2.39. And so real quickly, okay, so 2.3 in the very last column will be 0.09. Okay, so that's 0.9916. Let me see that. There you go, 0.9916. And then somehow we're going to have to get a p-value from that. So don't forget, 9916. That's the area to the left of 2.39. We need the area to the right. So this is going to be 1 minus 0.9916. Like that. So let's figure out what that is. And again, just keep in mind we're counting both tails on this two-tailed test. So this is going to give us one of the tails. Let's double check on what this comes out to be. 1 minus 0.9916 is 0.0084. That's not the p-value because, again, this is a two-tailed test. So let me just denote the other side is also a 0.0084. Okay, so you got to double this. So it's going to be 2 times 0.0084. And that'll be pretty small. So I think I've got this up on the screen. I'm just going to say times 2, enter. So 0.0168. That. Okay, so the p-val is, once again, I'm just going to focus on the first 2 digits here. The last 2 digits really don't have much bearing. So 0.01, and comparing that to alpha, which is 0.05. 0.01 is definitely less than 0.05. And less means we reject the null hypothesis. We keep rejecting. But here we go again. The less means reject HO. and support H1, which had said that if you look back that mu is not 24, we're supporting that. Okay, so we'll just kind of wrap this up over here. Okay, so p-value 0.0168. Like that. And that's great. Just a quick reminder, you should grab the dot when you move the test statistic. So sometimes the test statistic, it comes out negative, but the dot won't ever be on the left. It'll always be over here, and you have to drag it to the left like this if you want a negative test statistic. This one's positives, and I have to move it to 2.39, so here goes. Right there, 2.39. So it says the area of the tail is 0.0084, which is what we said, but we have to double this, so the area is the p-value is 0.0168, which is what we got. Okay, it's less than 0.05, so we're rejecting and the null hypothesis and supporting the alternative. Okay, we reject the null and support the alternative. We don't like to talk about the null hypothesis because we're not trying to prove that. We're trying to prove the alternative. So the alternative says that the mean is not 24, and we are supporting that. Okay, so the data support the claim that the mean age of students at Mount SAC is no longer 24 years. That's that first one, just dead on. Okay, and we should be good to go. That's it for this section. Good luck, everybody.